Okay, good morning, ladies and gentlemen. I'd like to first thank you all for coming today on this special day where we're going to be defending our thesis, Abnormality, Localization in Chest X-ray Scan, supervised by Dr. Hossam Sharara and Dr. Mohamed Moustafa, presented by my colleagues Abdullah Muhammad, Abdullah Nashat, Mohamed Ebrahim, Omar Ali, Youssef Zoheiry, and myself, Aly Zidan. Okay, first I'll take you through our agenda. We're going to start by our problem statement and the motivation. Then we're going to go through to the initial survey, followed by our base model. We're going to try explaining our base model. And then we're going to go to the data set that we put together to train our model. Then we're going to look at the results, followed by the app design and architecture. And then we're going to go through the app demo and the business plan. Okay, starting with the problem statement and motivation. Our problem statement is that in the surge of demand for X-ray scans, the increased workload has caused the results to take a prolonged time for the processing and with the increased possibility of human error. Followed by our project motivation, mainly it was for time reduction. As we said, a machine is much faster. Followed by error minimization. So as we said, we eliminated the human error. And again, we have a reduced cost as a number of radiologists have to be on paychecks. Okay, these are some simple statistics. We have more than 8.5 million daily X-rays around the world, with 85% of the people have at some point had their own X-ray. And here we have a statement by award-winning Professor Jeffrey Hinton, where he said people should stop training radiologists now. It is just completely obvious that within 5 years, deep learning will do better than radiologists. Stated 2016, he's the winner of the Turing Award.
So at the start of our project, we studied and surveyed the available literature extensively to get a good grasp on how our topic was being addressed and worked on within the industry. We also wanted to visualize and get a good understanding of how our contribution can be significant and relevant within the context of the literature we saw. We also wanted to figure out that almost all research and all the literature that we surveyed was fixated on the concept of image level prediction and for the picture as a whole, and it lacked the data and information on the concept of localization. So localization is the identification and position finding of abnormalities in radiology images. Localization is potentially hugely beneficial and can be life-saving if it is designed to support radiologists in their work. This when we first started noticing and employing the concept of localization to be an essential and main part of our contribution. In our research, we came to the conclusion that there was a general tendency in favor to deploy explainable AI techniques, as the literature mostly agreed that explainable AI is more efficient and reliable for radiologists. This is particularly significant as explainable AIs show radiologists not only the final results, but the methodology and how the results were obtained in the first place. This gives the user the ability to review results quickly and efficiently, making it a trustworthy, effective, and efficient option. There's some of the state-of-the-art models that we researched and compared. They include models like AlexNet, UNet, AnaXNet, and DCN. Now, Omar will explain the baseline model.
So for the baseline model, so it shows HAM model as our baseline. It stands for hierarchical attention mining. It was not the state-of-the-art model, but it was the best that we could obtain. So it was pre-trained on NIH chest X-ray 14 dataset, which is composed of more than 100K images. It used ResNet 50 as its baseline model and contained 3 levels of attention mechanism: foreground attention, positive attention, and abnormality attention. So that's a brief overview of what the HAM architecture looks like. It begins with excluding the negative images from the dataset, and then goes through two stages to localize and classify the abnormality or the pathology in the image. So for the datasets, we obtain 3 datasets, Shakespeare, which is composed of more than 200,000 chest X-ray images. These images were automatically labeled using ruler-based labeler. And we have also Vinbic data, which is the most recent one. It contains more than 18,000 chest X-ray scans. Each scan is annotated by 3 radiologists, except for the test set, which was annotated by five radiologists. The last one is NIH, which I mentioned earlier. It contains around more than 100 K images, and the labels were mined from NIH back systems. So our custom set, chest X-ray, Chexpert and NIH both had some automatic, most of them were automatically labeled, but they also had some manually annotated images. So we gathered the manually annotated images from Vimic data from Chexpert and from NIH, and put them all together. We also used the technique called weighted box fusion to because the Vinbic data set, each image was annotated by three radiologists, so it had a lot of bounding boxes for each label. So we tried to reduce the amount of labels per image to one bounding box per image per label per image. We also merged the similar labels and dropped the least frequent one. And the final set contained around 18,000 labeled X-ray scans with 20 different labels. So for the results, we did not adjust the architecture itself for the ham model, but we tried it on the new data set. We achieved a slightly lower AUC score, but slightly higher IOU score. As I said, the NIH dataset, which was the initial dataset the model was trained on, was labeled automatically, and we were advised not to use it because it's not a good practice. That's why we stick to the new dataset, even though it was it produced a lower output. So let's continue with this app demo.
Okay, so for the app demo, the user, can you post please for the app demo, the user basically the user starts the application. So he or she has two options, either signing in or signing up. And after taking the credentials of the user, assuming that it is saved beforehand. So then move to another option, which is the sign up page. Then after signing in, the user will move to the radiologist will move to the next page, which has the list of patients. So each patient has like an ID or a unique ID and name, mobile, and action. And the action basically takes the user to another page, which has like the patient info and has like different features like uploading the scan on the patient profile. As you see, the API is actually fetching in this. So it has all different scans, and so the user can actually add a scan on this patient. So the model here is actually analyzing. So for example, this case actually shows no finding in this image. Uploading another scan. So takes time for just processing. Actually, no find again. So I guess we skip this part for the app demo. For so Abdallah will continue on. This is the result for the final test case. Now let's go to the demo for the mobile app. Our app is a multi-architecture app. It consists of 3 main activities. The first activity, which is the login page. It contains a text box for taking the user input and buttons. When we click on the create account, it opens another activity and it collects the user information for creating a new account. Once the login button is clicked, a token will be generated in the backend and associated to this specific user. The user can access any API in the backend only using this token as an authorization bearer token. This is for security features. This list contains the list for the patients that the user have. We can filter and look for the patients by name. Also, once we click on one of them, it opens the patient profile apps. It contains the multiple scans. Once we click on a scan, it opens, but this scan is not included in the database. Okay, we can add a new scan. Now we're selecting a scan and we clicking submit. It takes a few time while the model is processing the image. Okay, now this is the output, and the output is no findings. The model couldn't find anything in this image. However, once we have the output, the output labels will be colored according to the colors of the labels in the image. Okay, let's move to the business plan.
Now with our business plan, with our company purpose, as the first Egyptian service provider of an AI medical diagnostic tool service, we aim to capitalize and gain the trust of our potential local market segment with competitive and more affordable solutions to the international alternatives available in the market. Our company vision and mission is that we want to provide an easily accessible medical diagnostic tool with competitive costs and efficiency, which would help cut down the costs, decrease the amount of human error in the medical diagnosis process. In regards to our market plan, we first had to realize who is our buyer persona. Our initial market research was conducted based on using other online platforms that summarized who the medical professionals who registered on other digital services in Egypt were, in addition to using the statistics provided by جهاز التعبئة والإحصاء, which summarized who are the doctors and hospitals who worked in private and public institutions in Egypt. And this is the summary that we believed was viable and worked for our potential market. We have 600 private and public hospitals, and in addition, we have 15,000 doctors relevant to the fields we currently cater to, which are all chest-related abnormalities. Now, with our buyer, who his specific persona would be, our buyer is an individual or entity functioning within the medical field and can be holding a medical or non-medical position within the field. He or she themselves need to have medical expertise with the radiology or pathology fields, or have medical professionals working within their business who do have such expertise. Our buyer either does not have the financial capabilities to purchase from our international competitors or finds their offerings limiting to the specialties that they provide in their institutions. Our buyer finds our success diagnostic rates higher than their parallels in the international market, or and finally, the buyer's main challenge in their norm of the field is that they realize that the current mode of operation in the radiological pathology in Egypt is no longer viable to their business needs when there can be a more efficient approach. Now, with our positioning strategy, as my friend and colleague Ali said at the beginning, we rely on three main factors, which is time reduction, cost reduction, decrease of the human error. When it comes to the time production, our product will reduce both the working hours and workload of the radiologist and the time needed to intended for the doctor or the patient. When it comes to cost reduction, our product positions itself outside the normal diagnostic tools where it doesn't require the institution or the hardware and the software, which costs thousands of dollars for each piece of equipment, which our international competitors currently provide. Businesses can also cut costs by supplementing the radiologists with our tool and decreasing the amount of working time per scan. This would reduce the need for radiologists to work full-time for the same number of scans that would be needed without the use of our product, and would allow the radiologists to process much more results in the same working hours. This reduces the cost per unit scan, and also since our radiologists' time per scan decreases, the need for more radiologists to work has been resolved, and so if the business chooses, they can hire less radiologists with a higher output, which cut costs. Now, with decreasing the human error, according to research that we derived, we have gathered that a huge part of the error factor in the radiology field is considered human, and such error increase due to increasing workloads on radiologists. This can be easily solved with what our project aims to provide, because we decrease the radiologist's workload and support him in his diagnostic task. Now, with our services offered, we currently offer our AI diagnostic tool, which caters for 19 different chest pathologies. When it comes to our pricing model, we offer a hybrid model, which is a mixture between a value-based pricing and a tiered pricing. We have three payment tiers based on the size of the medical practice or institution that will be signing with us, which are either individual tiers, SME tiers, which are small, medium enterprise tiers, or large corporate tiers. When it comes to the competitive analysis, we have three main huge competitors in the international market, first of which Siemens Healthineers. Siemens' competitive advantage is that it is a diagnostic tool currently scaled to cater for more than 6 medical specialties. Siemens is a household name which would be able to penetrate any market just by its brand. But when it comes to its competitive disadvantages, Siemens' solution costs thousands of dollars to purchase and thousands of dollars to maintain a subscription to their tool. In addition, Siemens' diagnostic tool only works if purchased with synchronized hardware and cannot work irrespective of one of both the software or the hardware. The second competitor is Samsung Healthcare. Samsung's main competitive advantage is that it in addition is household name, but its competitive disadvantages is that the solution as well costs thousands of dollars to purchase, and in addition, just like Siemens, to be able to purchase and use a diagnostic tool, you have to have the hardware and the software. In addition, Samsung only provide diagnostics for one category of disease within the cardiothoracic surgery, which is the chest X-ray field, and has a 70% accuracy rate and a 20% false positive rate within that one cardiothoracic diagnosis. Okay. With our final competitor, GE Healthcare Suite, their competitive advantages are that they are the only AI-powered diagnostic tool that flags its scans and alerts the radiologists based on the severity of the scan, which is a metric defined by the hospital. In addition, Radiologists, if a case is flagged as a high risk by the medical institution, the radiologist would be able to prioritize that before other scans within the system. The GE suite connects the hospital's internal worklist system, so it connects to any other system within the hospital. But the competitive disadvantages that they have is that they only work with big household licensed hospitals, and the tool currently only supports just pneumothoracics, which is one subfield within the cardiothoracic field. The final disadvantage is that the pricing model that they currently offer favors clients with a huge medical admin count registered to the system. So if they have 1 or 2 working radiologists, the pricing model would not be able to cater for such a small business. That's it.